Alright, so separation of variables. And I think I may have given the wrong impression. And the last thing, you may incorrectly have heard me say I'm not going to test on the Euler's method. I think that's an overstatement. It could happen. Alright, anyway. So, separation of variables, let's get to it here. So basically, differential equation is separable if it has the form dy dx equals to g of x times f of y, where g and f are some functions, all right? In other words, you can separate the variables. So I've since then learned how to spell separate, I think. But anyway, so dy over f of y is equal to g of x dx, sort of formally. Then you integrate both sides, separate, integrate, I often say. And there you go. That's pretty much it. Now, let's look at an actual example, almost with numbers. Dy dt equals to k times y. So dy over y is equal to k dt. So I separate it to level of differentials, then I integrate both sides. Integral of dy over y is natural log of y equals to kt plus a constant. Well, shame on me. Goodness gracious, look at that. What is wrong with me? I have neglected my absolute value signs. That's going to get me into trouble. So then, of course, we get that the exponentiating both sides, we get that the absolute value of y is equal to e to the kt plus c, but I can put a plus or minus here to account for the absolute value. I'll put that plus or minus in here. And then we can just identify that e plus or minus e to the c is in fact y naught e to the kt. And there you go, that's an explicit solution. Now, if y of 0 was given to be 3, then you'd find 3 e to the kt, right? So you can see why y sub 0 is a good notation here. Now, for what it's worth, if k is greater than 0, we have exponential growth. If k is less than 0, we have exponential decay. Here's another example. Dy dx equals to a to the x plus y. All right, so first move is to separate, and so to separate this, I multiply both sides by a to the minus y, and then I multiply by dx, formally at least. This gives me integral of minus a to the y dy equals the integral of a to the x dx. We integrate. Remember, we got 1 over log a. Since a might not be the exponential, we got to account for that. And then what am I doing? I want to solve for y. So I called this thing c. So I have c minus a to the x is equal to a to the minus y. And take the natural log of both sides. That gives me minus y in that log a. And there you go. So y is equal to minus the natural log of c minus a to the x over natural log of a. Now, I would draw your attention to the fact that the solution does not look like, stuff plus a constant. It's important that when you do this integration, you add the constant there and you follow the algebra. Wherever the algebra puts that constant in your solution, it's where it's got to go. You can't just not add a constant here and then just hope it's going to work out. It won't. It won't work out and you'll be wrong. Got to add the constant when you integrate for separation of variables. All right. Another example. Du d theta equal to 2 theta plus secant squared over 2u. We want to find the solution with u of 0 being minus 5. So we separate. We got 2u du and 2 theta plus secant squared theta d theta. We separate it. Now we integrate. The integral of 2u du is u squared. The integral of 2 theta plus secant squared theta is theta squared plus tangent theta. And so that gives us an implicit solution. And of course I can solve for u. Take the square root, allow for plus or minus, of course. And so those are my solutions. Now, if I want u of 0 being minus 5, that means I have to choose the negative root. All right? And so there you go. U of theta is minus the square root of theta squared plus tangent theta plus 25. All right. So I'm just going to keep reading through a few more of these. I hope they, you really got to do them for yourself, but I'm just going to try to emphasize some important calculational ideas as we look through these here. Find an implicit solution to dy dx equals to cosine of x over y to the 4th plus y squared plus 23. And I said also find the equilibrium solutions. All right. So let's see here. So integrate, separate, and integrate gives me this quartic in y integrated and cosine of x dx. Of course, the quartic integrates to a quintic, and you can't usually solve the e. I mean, there's precious few of these you can really solve. I definitely cannot isolate y, so we have to be content with an implicit solution here. We don't really have a choice in the matter. I mean, I suppose numerically we could locally approximate y as a function of x with this if you wanted to, but anyway. Now, equilibrium solutions for this problem. We're looking for dy dx equal to 0, but also 0 is equal to cosine of x over that. So apparently my equilibrium solutions are going to be plus or minus like pi over 2, 3 pi over 2, and so forth, because that'll make this quotient be 0. All right. Now, I got tons of examples here to share with you, so let's just keep looking at them. Dy dx equals to 1 minus x squared over y squared, so we multiply y squared over there, multiply dx over there, and integrate both sides. Integral of y squared to y cubed over 3, and this integrates to x minus x cubed over 3. And then I have to add a constant. Now, you don't have to add a constant on both sides, but you got to add it somewhere, all right? And so that's an implicit solution, of course. Next up, dy dx equals to 1 over x y cubed, so we got y cubed dy equals integral dx over x. Hey, check it out, I learned how to take the absolute value when I integrate this time now. Yay, I learned. Integral of y cubed is 1/4 y to the 4th equals to the natural log of the absolute value of x plus a constant. That is the implicit solution. I suppose I could solve for y there if I wanted to, but I don't. Dy dx equals to y plus 2 times 2 plus sine x. So we have dy over y equal to 2 plus sine x dx, separating, and then integrating gives me log of the absolute value of y equal to 2x minus the cosine of x plus a constant. And, you know, again, unless somebody tells me otherwise, I am perfectly content to have a implicit solution as the solution. That's my default. Now, if your instructor says find an explicit solution, then you better do it. Explicit means we would solve for y, all right? Here we've got dx dt equals to 3xt squared, so I separate. I got dx over x equals the integral of 3t squared dt, which of course gives me log of the absolute value of x equals to t cubed plus a constant. So there you go. Solved. All right. Man, this stack is thick. I got a lot of examples here. We'll keep going. So here I have dy dx equal to secant squared over 1 plus x squared. So I separate and integrate. Of course, integral of secant squared, 1 over secant squared is integral of cosine squared, which we know how to do. And integral of 1 dx over 1 plus x squared is the integral, well, that's inverse tangent. So there you have it, folks. There's my implicit solution. Next up here, we have x dv dx equals to 1 minus 4v squared over 3v. So I separate all the v's to one side, all the x's to the other. Then I'm going to focus on the integration of the v because it's a little bit tricky. So make a u equals the denominator substitution, which leads me to this minus 3/8 du over u, which integrates to minus 3/8 natural log of the absolute value of u, which is that. And then, of course, the integral of dx over x is the log of the absolute value of x plus a constant. And there's your solution. All right. This one came with an initial condition. Again, separate, integrate, and then we plug in the data, which was y of 0 was minus 1. And so plug that in there and see what it tells me. It tells me c is 0 as it happens. So there's my implicit solution. Again, separate, integrate, right? Integral of 1 over square root of y plus 1 is a u equals y plus 1 substitution, which gives me that. Integral of cosine times 2 is 2 sine, so I've got that. And I'm also given that y of pi is 0 in this problem. So I plug that in, see where that takes me. 0 plus 1. So I get 2 plus c is equal to 0, which tells me that c must be minus 2. So there you go. Solved. All right. Man, is there any end to these? Goodness gracious. Here we have a differential equation written in the so-called Pfaffian form. And again, you can separate and integrate. And it gives you the solution 1/3 x cubed equals to y squared plus 4, because I'm also told that y of 0 is 2. So when I plug that into this general implicit solution, it gives me 0 is equal to minus 4 plus c, which tells me c is 4. All right. So I'll let you look at the rest of these. I don't think me talking through them is really going to do much more good for you. Just look and see if there's anything particular to. I mean, again, it's separate, integrate, plug in the initial condition. So you can't see where the initial condition's coming from as I've written it here, but they were given in the original problem that I got from a textbook, which I don't think is Stewart. This is probably from Nagel, Saff, and Snyder. Let's see here. Let's see, I don't really have much to say about that one. Again, separate, integrate, plug in the initial value if you got it, find the solution, separate, integrate, careful with your absolute value, of course, plug in the initial condition, fixes the constant, and, oh, here I also solved for y. Just in case you wanted it. Alright, so this is the implicit solution, this is the explicit solution. Now, this one here shows you that we can actually do some kind of sneaky stuff with physics. So you've F equals to ma, right? So mg is equal to ma, and a is dv dt. But if we wanted to, we could do a kind of sneaky chain rule and say, well, that's really dv dt is really dx dt dv dx, which is, as I like to say, b dv dx. So you got mg is equal to mv dv dx, which gives us the differential equation g divided by m is equal to v dv dx, which is pretty awesome because then we can separate and we can integrate. And when we integrate, if we say that v when x is equal to x naught is equal to v naught, then lo and behold we get this v squared is equal to v naught squared plus 2g times x minus x naught, which of course you may recognize as the so-called timeless equation from kinematics. All right. So here's just a sidebar on applications. I'm basically saying here that physics is differential equations. That's pretty much what I remember from a lot of physics courses I took, which was that we have a basic set of differential equations which describes physical laws we know it, and then we try to solve them. And that's a lot of what you do in undergraduate physics. Now, I think there's more to it than that, but it's not an overstatement to say that there is a differential equation at the heart of all of our modern theories of physics, at least at the moment. This problem is the falling raindrop problem, which is interesting. I say imagine a raindrop falling through a cloud and it gathers water as it falls, and let m of t be its varying mass. Further, assume that the drop gets bigger and it gathers more and more mass proportionate to its mass, so it's going to solve the differential equation dm dt equals to k times m. Now, we also know that the force is equal to ma is more generally dp dt, where p is momentum. And so when momentum, well, p is mv, right? But when the mass varies, then dp dt gets a mass varying term, dm dt times v plus m dv dt. This is actually the differential equation which governs the motion of a falling raindrop. And what happens is something happens that's really kind of neat. You can work this out with differential equations like we're doing. So this gives us dv dt is equal to mg minus, I've assumed that dm dt is km, right? So put that in there. And so we get mg minus km dv, the m's be canceling. So we get g minus kv as it happens, and then we can separate. because we divide by g minus kv, we multiply by dt, we got that separate, and then I decided to put the k over there, so I divided both sides by k. It gives me a let's see here. I multiply both sides by k, rather. Multiplying by k gives me that. And then I integrate both sides and exponentiate, and out pops this solution. I have v of t is c times e to the minus kt plus g over k, which is actually quite beautiful, because you can see as t goes to infinity, we get this term drops out to 0, and that term goes to just g over k. That's the so-called terminal velocity. And if we go back and look at our original differential equation and rewrite it, we could look at it as m dv dt equals to ma is mg minus kmv, and we could think about that term, which is coming from the mass increasing, as sort of a frictional term. And the terminal velocity happens when these balance out. When these are equal, then we have acceleration being 0, which means that we can't go any faster, right? And so, solving these being equal gives me that v is equal to g over k. So the terminal velocity actually happens when those forces balance from that viewpoint. But roughly speaking, this also explains why something like this explains why rain doesn't fall super fast. Even though it drops from a high cloud, right? Because it's always bumping into other raindrops and getting bigger, something like that. I'm sure that the actual story is much more complicated. Another interesting application is the problem of orthogonal trajectories. And so in orthogonal trajectory, let's just look at an example. So if we have a circle, and let's find the orthogonal trajectories for this family of circles. So what we do is we differentiate the circle equation, which leads me to dy dx equals to minus x over y. This is the differential equation, which takes concentric circles of the origin as its solution set. The orthogonal trajectory must have negative reciprocal slope to the circles, right? So we do minus 1 over minus x over y. So I'm going to solve dy dx equal to y over x to find the orthogonal trajectories to the circles. And so I separate this, and I integrate, and I get this, which really just tells me y is equal to, and to be careful, there should be a plus minus in here somewhere, right? Yeah, fine. Plus minus, plus minus, plus minus. So you could rewrite that as just mx, where m is just the slope, right? The orthogonal trajectories are, of course, lines through the origin. Those are the orthogonal trajectories to circles are lines through the origin. Here, I'll draw it in. So let's suppose the circles are pictured like so. Those are supposed to be, I'm trying to draw circles. I tried. Anyway, those are the circles, and the orthogonal trajectories are, right, we just found those by solving the related, but it's hard to stop drawing once you start. But those are the orthogonal trajectories. They meet the circle at right angles, right? So if you focus in on any one of these points here, you can see that we've got a right angle, and both they intersect at right angles in that sense. And we found that, I mean, of course, you could use common sense to say, well, of course, orthogonal trajectories to circles are lines through the origin, right? But we derived it with calculus. Now that might not be as easy for the next problem, right? Finding orthogonal trajectories to this set of hyperbolas. So first of all, I find the differential equation by differentiating implicitly. It gets me dy dx is equal to x over y. The OT, orthogonal trajectory, will solve minus the reciprocal of that. So I do minus 1 over x over y, which gives me minus y over x. Then I separate and I integrate. And what do I get? I get that y is equal to plus or minus c over x. So the orthogonal trajectories, so these ones are these guys, right? So here's the ones I just did. My initial ones were, I put is it a plus or minus? fine, I guess these can all be from C positive, but if you didn't have the plus or minus in there, these, the ones I did originally would be the, whatchamacallit. Some of these are like y equals 1 over x. Some of these are like y equals minus 1 over x. The minus 1 over x are over here and over here. Y equals x are like here and there, right? Anyway, the original hyperbola, x squared minus y squared equal to k, are things like this. And my picture is not awesome because this is just one case of k. There's also, there's also ones that are like this. I mean, my picture has limitations here because there are also these ones, and they should be, there's like asymptotes that both of the green hyperbolas should be approaching. All right, I don't think I can fix, my picture's not quite right there. It's okay, but the graphing of both kinds of hyperbolas is not awesome in this picture. All right, anyway, you can look at mixing tank problems, which are kind of neat. So we have some substance entering or exit a tank. So I suppose I have 15 kilograms of salt at time 0. I let y of t be the kilograms of salt at time t. And then so I have rate in minus rate out. So there is no input to the salt. I'm just pouring pure water in at 10 liters, and I'm letting well-mixed salty water exit at 10 liters per minute. So we do 10 liters per minute times the concentration, which is y divided by 1,000 liters, which gives me minus 1 over 100 kilograms per minute. So my differential equation is dy dt equals to minus y over 100, and separate, integrate, and I put in my initial condition, which was y of 0 is 15 kilograms, and so I get y of t is 15 times e to the minus t over 100 kilograms. And then you can figure out how much salt there will be after 20 minutes. After 20 minutes, you're going to be down to 12.28 kilograms. So I don't know, that's kind of neat, because if you just try to solve that with common sense, it'd be kind of tough. Probably could do it though. Probably could do it. Well, here's an RL circuit, which I'll let you learn about in your Physics 2 course, but I'll just describe the big picture here, which is that this is Kirchhoff's voltage law, and it is a first-order differential equation. In the current here, the R is the resistance, L is the inductance, E is a fixed source voltage like a battery, and I'm assuming it's a constant voltage in this problem. But you can separate and you can integrate, and you can solve for the current as a function of time. And kind of nice stuff happens here. As time goes to infinity, that drops out, and we just have E over R as the long-term current, which is corresponding to the fact that after a long time, an inductor looks like a short circuit. So if you know Ohm's law, it says that the current is E over R as time goes to infinity, and that's what we see in this solution. Pragmatically speaking, if you look at the time constant tau, which is L over R, after about 5 of those, this is essentially 0.01. So everything interesting happens in the first 5 time constants, more or less. Okay, I think I told you more than I should have about that one. Next up, in terms of applications, again, this is all separation of variables. You can study exponential growth and decay. Simple population growth is dp dt is equal to kp. We solved that before. We get solutions y equals to, well, p equals to p naught plus e to the kt if I did it in p. And we can talk about the if the population doubles in a given time, what's k? Anyway, I have some comments here about the fact that population models have been wrong again and again. Let's see here, what is this? Oh, here's a problem about radioactive decay of polonium, which is a made-up thing that I made up. So, look at that one. Then I would encourage you to read this. Here I talk a little bit more about like philosophy and physics and the problem of believing physical law is a law just because we call it a law, right? I mean, I think we see just part of what exists is the long and short of it. But anyway, I'll let you read this. I don't want to shortchange it here. Now, there's also more complicated population models like the Logistic Equation. This one has a so-called carrying capacity built in. The idea of this is that when population's small, then this term is essentially 0, and so we just have dp dt is equal to kp. But once the population gets close to k, then this is close to 1, and that makes the growth rate slow to 0, right? So in other words, p equals k is an equilibrium solution. It's actually an honest to goodness solution here as well. So anyway, you can draw a graph of dp dt versus p actually, and we get positive growth below k, and negative growth above the carrying capacity k. And since it's population, we shouldn't really talk about p less than 0, right? If you look at the second derivative, you could differentiate the differential equation, and you'll actually be able to factor it. So you got concave up solutions, concave down solutions, concave up solutions like that. And it's growing the fastest when p is 1/2 the carrying capacity. So here's some pictures of some solutions. We have the carrying capacity, that's the equilibrium solution. If your initial population is less than the carrying capacity, then it kind of grows up to that exponentially like that. There's points of inflection at 1/2 the carrying capacity for all these solutions, so it's like concave up over here, concave down over there, concave down, concave up, concave down, concave up. Okay, you get the idea. And above k, we just have the population decreasing until it decreases down to that carrying capacity. That's how the logistic population growth works. Now, so here's the actual math to solve. So all of that I was just doing was geometric. If you actually want to solve it, you can separate, do the partial fractions, then you can integrate, and after a little bit of algebra, you'll get to something like p of t is the carrying capacity over 1 plus ae to the minus kt. As t goes to infinity, what happens? This goes to 0. We got p of t going to k, no matter where we start. So, and here's a couple of explicit problems where I'm actually working out the carrying capacity and the growth rate given various data. Pretty much every time you try to model a population of a nation with these sorts of things, it fails miserably because it can't do things like predict, earthquakes, fires, famines, all of the sorts of things which can really make a very big difference in the ultimate population growth of some group. All right, anyway, enough about applications already. I hope at the start of this video you got a good sense of how we do separation of variables. It's actually very, I would say it's very straightforward and pretty natural. I will warn you, the next technique, the integrating factor technique, it's a little bit sneakier.